I'll give a quick presentation now about getting a bond angle from two bond lengths and a dihedral angle. So this is for the H2Si2 molecule. Here's some data that's given to us. The silicon-silicon bond length and the silicon-hydrogen bond length. Those are given to us. Notice that no bond angles are given to us. We have a dihedral angle, eta. That dihedral angle is between two planes. One of them is a plane containing the silicon-silicon hydrogen. There's a silicon-silicon hydrogen plane and another silicon-silicon hydrogen plane. So there's two silicon-silicon hydrogen planes. So that's like silicon-silicon hydrogen. Those three, they form a triangle. That triangle is in a plane. There's another silicon-silicon hydrogen triplet. Those three atoms form a triangle. That triangle is in a plane. There's an angle between those. That dihedral angle is given to us. And there's some bond lengths given to us. But to make a Z matrix, you all know that to make a Z matrix, you need bond angles too. So let's try to find some bond angles. Hydrogen, silicon, hydrogen, for example, that's a bond angle that's not given to us. And if we want to find it, given the data that we have, this is nothing super advanced. It's nothing that requires like university level calculus or anything like that. It's just like elementary school geometry, but it is a little bit complicated. So let's try this now. So here what we have is the cosine law for dihedrals, or the law of cosines for dihedrals. Most of you are familiar with the ordinary law of cosines, or the ordinary cosine law. There's also something called the spherical law of cosines. This over here is the dihedral law of cosines, which can actually be derived from the spherical law of cosines. So here's the dihedral law of cosines, and it says that if we have a polyhedron, in this case we have a tetrahedron, we have just 4 atoms, so our polyhedron is a tetrahedron, but this will work if you take 3 faces of a more complicated polyhedron, like an icosahedron or a dodecahedron or whatever you want. So we have a tetrahedron with 3 faces that meet at a common vertex P. So there's edges AP, BP, and CP. And we have 2 faces, APC and BPC. There's a dihedral angle between these 2 faces. And with all of that information, we can find the dihedral angle phi based on all of these angles over here. So here's our molecule, H2Si2. We are given some bond lengths, and we are given the dihedral angle between 2 Si2H planes. So one of those planes, I have silicon, silicon, hydrogen. If I take the 3 purple dots, the rightmost 3 purple dots, I make a plane out of those 3 dots. Then I have one of the silicon, silicon, hydrogen planes. And if I take the 3 purple dots on the left, the leftmost 3 purple dots, I have another triangle, and that's another one of the silicon, silicon, hydrogen planes. So we have that dihedral angle, and we have some bond lengths, and now we want to find some bond angles. So the first question is, how do we label AP, BP, CP? How do we label all that stuff? So we know that we have the dihedral angle between the faces containing APC and BPC. So hydrogen, silicon, silicon, hydrogen, silicon, silicon. We know that there's only 2 silicon atoms here. So those must be the P and C, right? Because silicon, silicon, there's 2 silicons here, there's 2 silicons here, there's 2 PC. We know that that has to be PC. The one thing changing is the hydrogen. We could have this hydrogen or that hydrogen. So one of these faces is with the left hydrogen, one of them is with the right hydrogen. So that would be the APC versus the BPC. But since there's only 2 silicon atoms, we know that the 2 silicons have to be the PC. Okay, so let's make silicon, silicon equal to PC. And one of the hydrogens is A, one of the hydrogens is B. So now we can label our tetrahedron. We have a common vertex P. That is one of the places where the 3 faces meet each other. That's the common vertex P, where 3 faces of the polyhedron meet. And then we have the other C is, of course, silicon. And then we have A and B are the hydrogens. And due to symmetry, we can label it, if the left one is, if the left hydrogen is B and the right hydrogen is A, that's okay. If this silicon is C and that silicon is P, that's okay because of symmetry. For other molecules, it might not be that simple, but that's what we have here. So this is the law of cosines for dihedrals. We have eta equals the inverse cosine of this big thing over here. And now I've labeled, we have, instead of APC and BPC, we now actually have some bond angles here. And in this case, notice that we have the angle H silicon-silicon and H silicon-silicon. If we didn't have such symmetry, if we didn't have the two hydrogens, those two corners have both hydrogens. If we had instead hydrogen and deuterium, that's a different isotope of hydrogen, then these two bond angles might be different. And so we would have to use the full cosine law for dihedrals. But because we have two hydrogens at the corners and two silicons at these two corners, we can actually deduce that these two angles are the same. The H silicon-silicon angle is the same. So basically we have cosine squared of phi and sine squared of phi. So we have a much more simple formula here. I've just said hydrogen silicon-silicon is the angle phi. Hydrogen silicon-hydrogen, that's the angle theta. That's what we're looking for. So we have this triangle here where we have defined phi here. We have silicon, hydrogen, and silicon. That's the angle between those three atoms. We were given the hydrogen-silicon bond length, so that's R2. And this hydrogen-silicon bond length is also the same. That's also R2. R1 is a different bond length that was also given to us. Silicon-silicon bond length was given to us. So we have three sides of the triangle, and we have an angle. We all know that if we have three sides of the triangle, the angle, all of the angles are known because we know all the side lengths. Basically, if you try to draw that angle, if you try to draw that triangle with these side lengths, you'll be forced to have a certain angle there. So then we can use the ordinary law of cosines to find that angle phi. So we just have R2 squared equals R2 squared plus R1 squared minus 2R1 R2 cos of phi. We can subtract R2 squared from both sides. We can divide R1 from both sides. We can divide both sides by R1. R1 is not 0, so it's okay to divide both sides by R1 because that bond length is not 0. And then we just isolate for cos of phi, and we get R1 over 2R2. So this cos squared of phi, that's easy to find. Sine squared of phi, does anyone have any ideas how to find sine squared of phi? I'll mute myself for a second if anyone wants to answer that.
I mean, once we find cos of phi, isn't it like quite straightforward to get the sine of phi as well?
It is, and that's why I'm trying to see if people are awake. Like, is anyone able to?
Minus cos square of phi.
Yeah. Okay. Good. So one way to do it is cos squared of phi plus sine squared of phi equals 1. So and then you just rearrange it to get sine squared of phi. At first, when I did this, I actually did it a slightly different way. I said cos of phi equals R1 over 2R2. That's what we got right here. So we got that. And then we also know that cos of phi is equal to adjacent over hypotenuse. So I just created an angle. I just created a triangle with that as my adjacent and this as my hypotenuse. And I used hypotenuse squared, square root of c squared minus b squared equals a squared, okay? So this is just 4R2 squared minus R1 squared, all square rooted. That's going to be the opposite side, and sine of phi is going to be opposite over hypotenuse. And then 2R2, that is equal to the square root of 2R2 squared. So it's equal to the square root of 4R2 squared. Okay, if we square this, then the square root of the square is equal to the original thing. So we have now this entire thing, if we have square root in the numerator and in the denominator, then it's like saying we have the square root of the whole thing on the right side. So then we can just square both sides. We have sine squared of phi equals this thing on the right side. The left side, the first term is just 1. The second term is R1 over 2r2 squared. So this is exactly what Sukrit just said. Sine squared of phi is equal to 1 minus cos squared of phi. We got the same thing. So we plug this all into this formula. We have the dihedral angle eta equals this thing over here. And what's the angle we're looking for? We're looking for eta. Or sorry, we're looking for theta. We have eta as the dihedral angle. We want the bond angle theta. So we have to solve for theta now. And that's not too hard. We can multiply both sides by this. Well, we first have to do the cosine of both sides. Then we multiply both sides by this denominator. Then add both sides to this term over here. And then we do the inverse cosine of the whole thing on the left side. So we'll get some huge expression, but it's equal to theta. So we have a closed form expression for theta. I don't recommend trying to do that on your calculator because when you're typing in R1, R2, eta, all with 4 or 5 digits, you're going to make a mistake. And if you don't make a mistake, you might, the calculator doesn't have enough digits or whatever. Some people, what they do is they truncate the answer. They do pieces of it into their calculator, write down the answer to this piece, write down the answer to this piece, and then they plug it all into the calculator. But typically, people get the wrong answer that way. I used to teach at Oxford the biophysical chemistry course, and the instructor that had made the solutions for this problem set that the students were given, all the answers were wrong by small amounts. And I basically showed the instructors that they didn't know how to use a calculator. So this is the software I use for doing this type of calculation is Wolfram Alpha. It was made by a friend of mine by the name of Stephen Wolfram. Here's a picture of the three of us, myself, Stephen Wolfram, and Carlos Alfonso at St. John's College, Oxford, when he had come to give us a talk over there. He's very active on Facebook. I don't know if he's active on TikTok or Instagram or Snapchat or anything like that, but he's active on Facebook. And I really like this Wolfram Alpha software because I can just say solve for x. So here theta is x, phi is y. I can just say solve for x and it gives me this solution over here. X equals this right here. And I can also type in values for x and y and it will give me the number. It's better than trying to calculate everything on a calculator. There is a danger with Wolfram Alpha. Notice the difference between the left side and the right side. So here on the left side, I have cos of eta equals this thing on the right. So on the right side here, I have I've just typed in this equation that I wrote down here. Eta equals cos inverse of cos of theta minus cos squared of phi, all that stuff. So I have that here. On the left side, I've done the cosine of both sides. So I have cosine of eta equals this. So when I did it this way, the original way, I just typed it into Wolfram Alpha, I got some complicated answer where it's saying that if the real part of the dihedral angle is 0 and the imaginary part of that dihedral angle is bigger than 0, then you have this. And if the imaginary part is 0 and the real part is, there's all this complication there. And I don't even want to try to imagine what it means for a dihedral angle to have an imaginary a real part equal to 0 and an imaginary part bigger than 0. I don't want to try to figure out what that means. On the left side, when I did the cosine of both sides manually, I got the right answer, just theta equals this. Okay, so there is a little bit of danger with Wolfram Alpha. It's not like you can just type in your problem. Nowadays, it's not Wolfram Alpha. Now you're using ChatGPT, right? But you have to still know how to use ChatGPT or how to use Wolfram Alpha. So that's where the skill comes. And likewise, now if I type in, I solve for phi, right? Phi or cosine of phi was equal to R1 over 2R2. From that, we got sine of phi. So if I type in this R1 over 2R2 and I put that in for phi, or sorry, cos of phi squared is equal to this here, and sine of phi squared is equal to this, then again, it gives me all these different cases. Like if the real part of the bond length is less than 0, then this is the answer. But the bond length is not less than 0. So we know this is just a really complicated answer, unnecessarily complicated. So what I'm going to do here is I say R1 is bigger than 0, R2 is bigger than 0. So now I have solve this equation here for theta, given that R1 is bigger than 0 and R2 is bigger than 0. And still it gives me 4 solutions. But this isn't too bad. Here, R1 is bigger than 0 in all cases. R2 is bigger than 0 in all cases. And then it's just a matter of like whether R1 is bigger than R2 or if R2 is bigger than R1, that kind of thing. And most of these are just... Anyway, I'll move on with... I can say most of this is just like 2 pi n minus this or 2 pi n plus that. So when you have an angle, you can add 2 pi, 4 pi, 6 pi, 8 pi. You can always add that. And that's not a problem. So here we have, I think what I just did next was I just said R1 equals this and R2 equals this. So now it's no longer giving me these cases like R1 is bigger than 0 and R2 is between 0 and half of R1. It's no longer giving me these cases because it now knows what the relationship between R1 and R2 is. So I gave it R1 and R2, and here's the answer I get. It's down to 2 cases now. Theta equals this times n minus that, or this times n plus that. This 6.28, that's just 2 pi. So 2 pi n minus this, or 2 pi n plus that. And I guess it's okay to say n equals 0. That's one valid solution. Alternatively, we could have n equals 1, n equals 2. We can get different bond angles. And it's like one of them... Yeah, so if we make n equals 0, we'll get negative this and positive that. So we'll get 2 different answers, negative this and positive that. We have to make sure that this eta angle is also typed in radians, even though they gave it to us in degrees in the book. In Wolfram Alpha, we have to put it in radians. Then we convert back to radians, we get 72.555 degrees. Okay, so that's the final answer. Or we could have said it's negative 72.555 degrees, and that's just like... For every bond angle, you can have 360 minus the bond angle. It's still a bond angle. Okay, so the final answer I got was 72.555 degrees. And there's another way to do this, which I'm going to get Justin to present. This is a way to do this calculation without the law of cosines for dihedrals. So we just completely eliminate that dihedral law of cosines. So Justin, you're here. I can mute myself and I can let you speak now.
Should I just share my screen?
You could do that, or I can change the slides for you whenever you say next slide.
Yeah, that would do. Okay. So the equation we just used, the dihedral equation, so obviously that just comes from a horrible load of trigonometry. But actually, in this particular molecule, there is some symmetry that would greatly simplify things. So here I'm just going to start from scratch and try to find the HSIH bond angle. So if we stare long enough at this molecule and imagine ourselves looking at the molecule along the red arrow here. Next slide. This is actually what we'll see. And one of the silicon atoms is behind the one in front. I hope this makes sense. And theta here is the dihedral angle that is given. And blue dots are just the hydrogen atoms. Yeah, next slide. Right, and this is the view we will get if we just tilt it downwards a bit. So here we see the silicon atom behind the front silicon atom, if that makes sense. And we'll see its 2 planes, which is the HSI-SI plane, and the angle between the 2 planes will be the dihedral. Next slide, please.
Perhaps I can just ask this angle theta, because I don't know if you said this. So there's 2 diamonds here. There's 2 silicon diamonds. Mm-hmm. So that angle is this angle over here, or it's this angle over there?
It's the angle between the 2 planes. So it's not exactly the HSIH angle, because that's what we're trying to find.
Okay.
But it's the angle between the 2 planes.
So this diagram here, to me, it kind of looks like a bond angle, right? It's you have hydrogen, silicon, hydrogen, and an angle between them.
Yeah, I guess so. But
yeah.
It should be more apparent in the next slide.
Okay, so just a warning to everyone, this theta is not the bond angle, it's actually the dihedral angle between the two planes.
Yeah.
So that could maybe be drawn slightly differently, but I'll go to the next slide, maybe that will make things a little bit more clear.
Yeah, so A here is what we're trying to find, and the gray plane is the HSIH plane, if that makes sense. So here we would like to find actually the HH length, and because that would be very useful. If we know the HH length, then we can automatically find the HSIH bond angle. Yeah, next slide, please.
So how about this? So how do you know that? How do you know to use this gray triangle instead of this H silicon H triangle? This other. There's a big triangle and there's a small triangle, right?
Yeah, they are identical.
Okay.
Because as you can see, one of the silicons are drawn slightly bigger.
Yeah.
So that's the one in front, that's the one at the back, and they're actually the same triangles.
Yeah, so basically due to symmetry, they're the same triangle, so you could have used either.
Yeah, so it's like two flaps in a book, if that makes sense. And the SI is the hinge.
Yeah. Okay, next slide.
Yeah. So here perhaps it's more clear where theta is. So it's actually, it sits in the middle of the HSISI plane. And if we can calculate the hypotenuse of this right angle triangle, then we can calculate the HH bond. And if we have the HH bond, then we can find what we're trying to look for, which is the HSIH bond angle. Yeah, I hope that's clear. So next slide, please.
Yeah, and I think you've already answered the question of how do we know where to make the corner of the red triangle. You said it's in the middle of the silicon-silicon bond.
Because it's all symmetric, so it's easy.
Okay, so the dihedral angle is basically the angle between hydrogen, and the middle of the silicon-silicon bond. Is that what you're saying?
Mm-hmm. Yeah.
Okay, next slide.
Right. And the only unknown in that triangle is the green line. So we'll try to find the green line next. Yeah, so I think, yeah. And then it's just some elementary trigonometry that links the green line to the final answer. So this is just retracing our steps back to A, which is the bond angle. And that's the final formula we'll get. And you'll have to trust me on this. It does indeed yield 72.555 degrees.
Yeah, and we worked it out over the week. We actually calculated, Justin calculated 72.555 degrees, and I calculated it using the other formula, and we both got exactly the same thing. At the end, you said we have to trust you on this. If you had used Wolfram Alpha, then the trust component of it is a lot smaller. You can just send someone a URL to the Wolfram Alpha link, and they can just see it in front of their face. There's nothing to doubt about. So, and even this formula itself, we don't see, like in my formula, I just got it from Wolfram Alpha by saying, solve this equation for theta, and I gave these three values. So unless you don't trust Wolfram Alpha, then you probably trust that the 72.555 degrees is correct. Here, where this formula comes from, we don't exactly know. So even these elementary steps, like getting this angle, getting that angle, that can also all be done in Wolfram Alpha. So yeah, that's another way of getting the dihedral angle. The thing I worry about in terms of teaching a computer program how to do it is that the computer program is going to know, it's going to have to know that the dihedral angle is the angle between the hydrogen and halfway between the silicon bond. I don't know how to teach that to a computer, whereas with my method here, I just used this formula. And I plugged in, this is silicon, hydrogen, silicon, hydrogen, silicon, hydrogen, silicon. We're looking for this angle. We know these angles. We just plug in the angles. We plug in the bond lengths. And from there, well, we plug in this formula into Wolfram alpha. It tells us that if we know phi and we want theta and we know eta, we solve this equation for theta and we just get theta equals this. And then we just plug in the bond lengths and the bond angles and, the bond lengths and the dihedral angle, and we get this bond angle x. So I think it's a bit easier for a computer to do, but I think this was also a very elegant solution as well, because it doesn't require that dihedral law of cosines at all. It only requires like elementary school cosine law, Pythagorean theorem, right? Okay, so for this coming week, I have some more examples here that I think would be very interesting to look at in terms of developing this software that we want for generating Z matrices from this type of information. So sometimes they give us bonds and bond angles and we can make the Z matrix from there, and we have to find the dihedrals. Sometimes they give us the bonds, the bond angles, and the dihedral angles, and we'll have to find some of the bond angles ourselves. So that's what the software has to be able to do. And so for the people in this room, one thing I'd like you to consider for this week is, instead of hydrogen, silicon, hydrogen, which I just showed you, now we have, instead of two silicons, we have a sulfur and an oxygen. And here we're actually given some bond angles. We're given 3 bonds, 2 bond angles, and a dihedral angle. But notice that we haven't been given the HHO or HHS, so hydrogen, oxygen, or hydrogen, sulfur angles. Those angles are not given to us. So I'm asking you to solve the pyramid. We all know the term solve the triangle. They give you an angle and 2 sides and you have to find the other side or something like that. I haven't found this solve the pyramid term. I haven't found it online. I was looking for it. I don't know if other people use this term. But basically what I mean by solve the pyramid is we have some bond angles, a dihedral, some bond lengths, and we want to find the rest of the bond angles or the rest of the angles. Or maybe they give us the bonds and some angles and we have to find the dihedral. So solve the pyramid here. That's one problem to do. Another example is here we have the hydrogen-oxygen bond angle is given. And we are given some bond lengths. But it looks like we are not given, we're also given a dihedral angle of 120 degrees in 1 minute. So that is given to us. But we're not given the hydrogen, and hydrogen, oxygen bond angles. Or those aren't even bond angles, but they're just angles. We haven't been given those. So, and they've given us 2 dihedral angles. That's because this molecule happens to be a ground state doublet. Chemistry students will probably know what that means. Physics students will know what that means by the end of their degree. Chemistry students probably know it by now. But basically a doublet is 2 states, okay? So there's a lower level and an upper level of this doublet state. The doublet is just due to this, the configuration of the spins. The electron spins in the molecule have certain configuration that causes it to be a doublet molecule. So there's an upper level and a lower level. Let's just use this lower level. That's the lowest energy state of the doublet. And given this dihedral, this bond angle, and these 2 bond lengths, let's find these 2 angles. So perhaps next week, I think these solving the pyramid, it takes like 20 minutes or so. I don't know how long it takes, but maybe next week we can have a presentation from 2 of the students just to get more people involved and get people practicing some more of this. Sukrit has already given a presentation. Justin has already given a presentation. Maybe 2 of the other people in this audience can volunteer to do one each, one of these. Who wants to do hydrogen, silicon, oxygen, hydrogen? In the chat, I see that Payleen has said that she can. If no one else, yeah. So Payleen, you want to do the first one, hydrogen, silicon, oxygen, hydrogen? How about this hydrogen peroxide? Is there anyone that can do that? Egen is typing. Okay, good. So we have 2 volunteers. That's good. I also went through this book with all the geometries, that geometry database book. And it has a lot of different molecules there with bond lengths and bond angles and all sorts of information. And to construct the Z matrices, often we have to complete the pyramid. So I've now organized all 4 atom molecules based on their shape and point group. Who here knows what a point group is? I'm asking you, you can just say it in the chat if you don't want to unmute yourself. Who here knows what a point group is? Jen is typing something. You just have to type yes or no. You don't have to type a full sentence. Okay, now Jen has stopped typing. Yes, okay, so Mia knows. I figured some of the chemistry students would know what a point group is because that is usually taught in the inorganic chemistry class, and then in Oxford, the second year quantum chemistry class, at least when I taught it, there was 4 weeks of group theory. Yeah, the chat is a little bit hard to find. It's in the top right corner on my browser. For other people, it might be in other places. Okay, so there's 2 people that know what a point group is, 1 mathematics student, 1 chemistry student. Physics students will probably learn it in their graduate level particle physics class if they take it. Yeah, exactly. Symmetries. Well, Egen, you probably learned group theory in a much more mathematical way. You probably didn't learn it with this notation, like C3V, D3H, like these dihedral groups, and you learned what a dihedral group is, but not with this notation, so there's probably a little bit of learning curve even for the mathematics students here. But basically, this is just a way to classify the molecules based on their geometry. And so for 4 atoms, there's various different types of geometries we can have. We can have regular pyramidal, like P4, it's 4 of the same atom, so there's a lot of symmetry there. So we just have a regular pyramid, and the dihedrals are just given by cos-inverse of 1/3. For these pyramidal molecules, you can have different dihedral angles depending on if it's C3V or CS. These are all just coming from the general law of cosines for dihedrals. And then in the case of H2 silicon 2, we had that 2 of the angles were the same because of symmetry. So we had that these 2 angles were the same. So we just had cos squared of phi instead of cos of phi times cos of the other phi. And then when phi and theta are equal to the same, then we just factor out one of the cos of theta. We have cos of theta times 1 minus cos of theta. That's the same as what we have here when these 2 angles are the same. So there's various different angles we can get. When the point group is C2H, we have a planar molecule. I think all C2H molecules will be planar, so that's either 0 or 180 for the dihedrals. So I've tried to classify all 4 atom molecules. I've also done this for all 5 atom molecules too. This will be useful for the software. And there's 3 cases here which I think are a little bit more interesting. And so anyone that didn't volunteer for the first 2, maybe you can volunteer for the next 3. So here what we have is HCl, HCl. 2 HCl molecules. We have an HCl bond length and another HCl bond length, and these 2 HCl molecules are so far away from each other that I guess they're not even bonded to each other. So these bond lengths are hardly affected by that. And so what we have is a center of mass between this molecule and this molecule that's given to us. There's some angles, theta 1 and theta 2, with respect to this axis. And then there's an angle around that axis, 10 degrees or less than 10 degrees given to us. So based on that, we want to complete the pyramid. We have 4 atoms. Whenever you have 4 atoms that are not forming a plane or a line, we have a pyramid. So complete the pyramid there. Likewise, we have HF, hydrogen fluoride times 2 hydrogen fluoride molecules. We have a fluorine-fluorine bond length, I guess, and we have theta 1, theta 2. Don't worry so much about these alphas and betas. So we have hydrogen, fluorine, then hydrogen, fluorine, deuterium, fluorine, deuterium, fluorine, deuterium, fluorine. So these are just different isotopes, right? And on a molecular level, they're called isotopologues. So different isotopologues of the same molecule. We can just ignore deuterium for now. So just pick the first alpha, the first beta, and so we have the alphas and betas are given to us, and then the question is, how do we make the Z matrix for this? What are all the bond angles and dihedrals that are not given to us? Let's get those. And likewise here we have argon 2, the argon dimer connected to HCl, and we're given a bunch of geometry data here. So the argon-argon bond length, the argon 2 dimer has a center of mass. The HCl dimer has a center of mass, and then there's a distance between those two. Then there's a distance between the argon dimer center of mass and the chlorine, a distance between the HCl center of mass and the argon, and a distance between argon and chlorine. So, and then they've given us some angle beta. So that's 3 more molecules. So anyone that didn't volunteer for the first 2 molecules, I guess they thought that if they didn't volunteer for those, then there's nothing else remaining. But so we've had Payleen and Ejen volunteer so far. Justin has already given a talk. So I wonder if anyone else here, how many people do we have left? We have Michelle, we have Sukrit has already given a presentation. We have Arpit. Arpit, you're full-time this term, so maybe you could do one of these. And Tanch is with you too, right? You guys are both in the same room. So it looks like there's only 4 people left. That's Arpit, Tanch, Michelle, and Mia has already volunteered for something. No. She said yes about the point group, knowing point groups, but hasn't volunteered yet. So Arpit, you're doing... we have 3 people left and we have 3 molecules. So would it be okay if just the 3 of you volunteer to try to complete these pyramids for next week?
Sure.
So Michelle's okay with it, and then Tanch is with you, Arpit, right? Oh, Sam is here too. So who wants to do? So Arpit, you're doing Cl2H2. Arpit, Cl2H2. Tanch says we can both try, so you can maybe do HF2. And Michelle volunteered for argon 2 ClH. And I think Mia's the only one that hasn't volunteered, but that's okay because I think Mia knows all this stuff as a chemistry student. The other students are coming from engineering and physics, so you need more practice. Okay, so this next week maybe we can have like 5 short 5-minute presentations, just like go through all these molecules, because some of these are really interesting. They're not simple like the first 2 that I showed you. Okay, now probably what everyone is waiting for is the supercomputing tutorial. I'm also waiting for it. I haven't even I haven't gone through this crash course with Vandan yet. So let's try to do this. So how should we do it? I can open up a terminal.